about time to have today's seminar. And then I don't know, I have no idea, is it good or bad? We only have two presenters for today. Yeah. So you may have 1 hour or less than 1 hour seminar. Okay, so we can finish earlier. And then, so for first one will be 曾玉祥。You may start when you are ready.
final output of the forward kinetic function. In summary, target position, as shown in equation 22. Finally, to minimize the position error, the difference between the target and the current position is equation 24. Once the error is defined, we need to know how each joint angle should change to reduce it. To do this, we use the Jacobian metric, which links small change in joint angle to result change in the end effector position. As shown in equation 26 and expanding in equation 27, the Jacobian describes how each motor's movement affects the end effector to be placed. In short, it provides a linear relationship between joint angle, regression, and endpoint displacement. Since that way is highly nonlinear and the analytical Jacobian is hard to solve, instead we use numerical derivation by applying a small perturbation to each joint and measuring the change in end effector position. We can customize each partial derivative to form the complete Jacobian matrix. We use an imperative correction method based on numerical initialization to solve the IK. First, we set the initial joint angles and calculate the error. Then we build the Jacobian matrix. Use it to find the angles correlation and update the joint angles. This process repeats until the solution converges to the target position. To implement segment control, we simplify the Jacobian matrix and show in equation 34 during the global arrangement phase. We zero out the last three motors, focusing only on the first two. Using the update rule in equation 35, the system prioritizes scalable position through iterations, resulting in a more stable and human-like movement. Once the elbow is aligned, we shift our focus to the wrist, as shown in equation 36. We set the first two motors partial derivative to 0 to keep the elbow position fixed. The last three motors then take over to adjust the wrist position. The segmented approach simplifies the computation while significantly enhances the stability and initial length of the motion. This slide presents our stage 1 simulation result for our elbow position. We'll analyze the convergence performance through 3 key points. First, take a look at figure 8. You can see that the joint angle change for Q1 and Q2 remains smooth and stable throughout the entire motor. And moving to the position error plot in figure B, the 3D descent drop sharply, hitting a minimum with just 100 iterations. This theory demonstrates the efficiency of our algorithm. Finally, the elbow inclination plot shows the actual posture perfectly overlapping with our theory. Together, these results confirm that our approach achieves both precise positioning and highly accurate posture indications. With the elbow position secure, we now move to stage 2, wrist compensation. First, we already illustrate the joint angles for the final 3 motors. You can observe that three joint angles. One are the shoulder and two are elbow, as arrow matches. This process is divided into two stages. In stage one, the system takes the shoulder as a reference point and use the first two motors to align the elbow. In stage two, the remaining three motors align the wrist, completing a full arm motion reconstruction. The entire operation begins with the camera detecting the shoulder, elbow, and wrist joint in real time. This is our experiment result. Experiment simulated left and right arm swing, collect 30 data points per joint and across 50 strokes for 3 joint angles on each arm. After calculating the absolute error, the result shown in the table and the black bar indicate that the mean error remains between 7 and 10 degrees. This demonstrates good communication accuracy. Even with slight error from image recognition or eye-gaze computation, the robotic arm will track and reproduce human motion effectively and steadily. In conclusion, we developed the system that can imitate human posture in real time. Experiments show that the robot arm reproduces human movement accurately with good consistency and reproducibility. Overall, the system effectively and reliably replicate human motion. Thanks for listening.
Okay. So thank you for your presentation. I would like to open the floor for questions. Yes.
How do you align human coordinates from the camera with the robot?
We use relative mapping by setting the shoulder as the origin. We calculate relative factors. This cancels our deviation caused by different standing motion or body size.
Why is the arrow for the right higher than the shoulder?
Its error accumulation along the community chain. Also, the wrist is distal joint. It moves faster and is more prone to sensor noise or in the camera view.
Why split the control into shoulder to elbow and elbow to wrist?
It prevents posture disruption. If we solve ideal and at once, the wrist might reach the target, but elbow looks unnatural. This really ensures the robot posture truly meets these requirements.
Okay. Any other questions?
Is the interactive AK configuration too slow for real-time control?
Yes, we use the previous front angles as the starting point. Since human motion is continuous, the previous number shows more intended on the modern.
So I think we're going to invite the next presenter. Thank you. You may start when you are ready.
Good morning, everyone. My name is Iwan, and my supervising professor is Mr. Kailash. Today I will be presenting my research titled Lightweight Deep Learning Using Emotion Recursion Model. The main objective of this optimized architecture designed specifically for resource function edge device. By deploying this lightweight model, we aim to enable convenient robot to provide immediate autonomous with no support to society isolate individuals. The presentation will cover the research motivation and indeed analyze the purpose one-dimension neural network, the empirical result, and final the clinical application. First, let's look at the background of our research. The world population is changed fast by 2050. 22% of people will be over 60 years old. This engine change cause big problems, especially loneliness. Being lonely can quickly lead to brain decline and deep sadness. To help with this, we want to use convenient robot with music emotion recognition, or MER. Music is a great way to lower stress. If robot can understand music emotion, like how positive or strong the music is, they can help older people feel better without using medicine. Now let's turn our attention to our constraint and our core problem statement. Well, convenient robot like ASUS Zenbo Junior 2 are viable platforms for interactive care. They are highly resource-constrained edge devices. They are typically equipped with an Intel Cherry Tail processor, just 2 to 4 gigabytes of RAM, and 3,165 mAh battery. However, current state-of-the-art NER models rely heavily on massive 2D convolution neural network and deep RNNs, which require tens of millions of parameters and execute in the gigascale blocks range. Continuously running such computationally heavy model in the background will quickly deplete the robot battery and cause severe thermal throttling. Therefore, our primary research objective is to develop an ultra-lightweight regression model optimized for this platform without sacrificing accuracy. To overcome these computational bottlenecks, we propose a paradigm shift from heavy 2D spectrograms to a streamlined 1D architecture. As you can see from the overall architecture flowchart on this slide, our system pipeline consists of 5 key efficiency focus modules. First, NFCC extraction paired with a global temporal averaging strategy. Second, deploys separable 1D convolutional encoder to completely bypass 2D computation. Third, temporal convolution network, or TCN, integrate with an excitation model to capture long-range dependencies. Fourth, a multi-range feature aggregation head. And finally, generative adversarial adversarial network or game. This is optimized strategy. I will detail the engineer mathematics behind each of these models in the following slide. Next, into the data preprocessing and the lightweight feature extraction. Standard deep learning workflow need message to the time series matrix into the network. Instead, we extract 40-dimensional MFTC and apply a global temporal averaging strategy. Looking at the first equation on the slide, we average the coefficient across the entry time Xt. This really compressed the 2D matrix into a compact 40 by 1 vector vector. For feature extraction, we replace standard convolution with stepwise separable 1D convolutions. As demonstrated by the parameters comparison ratio equation. Using a large kernel size A, reduce the computational complexity by a factor or approximate 1 over k. This allows the model to extend its receptive path without the memory overhead typical associated with deep network. Moving on to the temporal model, we deploy a multi-scale temporal convolution network or TCN backbone. Although the temporal dimension was averaged during preprocessing, modeling the complex interdependencies between different acoustic frequency band remain crucial. To achieve this efficiently, the TCN used delay convolutions. The equation here shows how the dilation rate, which exponents increase as 1, 2, and 4, repeatedly expand the receptive cloud to capture long-range spectral correlations. Furthermore, we embedded 1Ds with an excitation model to generate attention light, allowing the network to dynamically recalibrate its feature maps, while scale residual connection ensure fast and stable conversion. After the TCN, the feature must be aggregate because distinctive emotional acoustic curves are complex distribute. A single pooling mechanism would lead to data loss. Therefore, we introduce a novel four-branch aggregation. Global average pooling capture macroscopic statics, while attention pooling extract silent frequency band. A compact BIGRU scans the frequency to model hierarchical harmonic relationships. most importantly, to capture the arousal dimension, we use a dynamic difference range. The equation on the screen calculates the absolute spectral flux. These actively measure the local energy gradient and the roughness of the audio signal, which strongly correlate with emotion excitement. These four perspectives are then fused through a shared dense layer. To address database and effectively improve the model accuracy without increase the parameters out of the final inference model, we introduce a gain assist optimized phase. During training, our regression model acts as the generator, while a discriminator evaluates the prediction against the true human net distribution. To condition the discriminator on continuous variables, we employ feature-wise linear model, or FILM, as governed by the equation. The continuous valence and depth arousal value are mapped into scaling gamma and shift beta parameters that directly modulate the intermediate convolution feature maps. These intergain and FILM mechanics in strictly confined to the training phase. The complex discriminator is discarded post-training, leaving a high precision, zero overhead inference model. Moving on to the experimental validation and hardware proofing. We value our framework using the continuous annotation of the EAM dataset. As the result table clearly shows, our proposed 1D-CNN and TCN architecture achieve state-of-the-art predictive accuracy on the EAM benchmark, reducing the valence RMSE to 0.125 and the arousal RMSE to 0.121, significantly outperformance at the 2D-CNN baseline. More importantly, the deceit of success lies in its age deployability. Traditional deep learning framework require billion of flops up to 14 gigascale operations. In stark contrast, our architecture requires only 0.603 million parameters and execute a more 3.08 million flops. This translates to computation load reduction of over 1,000 flows, shifting the workload from gigascale to megascale, while achieving supervised accuracy. In conclusion, this research represents a definite breakthrough in active computing for edge robotics by fundamentally comparison acoustic feature and utilizing a highly optimized 1D like with gain assist FILM optimized. complex bypass the hardware limitation of embedded system. Beyond algorithm optimization, this architecture has profound clinical significance. It enables alien robot to autonomously assist auditor environments and instantly personalize music to alleviate agitation and psychologically distress in dementia care patients. Future research will focus on multimodal fusion, combining this accused framework with facial and speech recognition and conductive the human-robot interaction choice in geriatric care environments. Thank you for your listening.
Thank you for your presentation. Okay, so I will open the floor for questions.
In the processes that we choose to use multi-dimensional NSCCS combined with robust neural averaging, could you elaborate on why, especially since the averaging losses neural information?
NSCC mimics human hearing. Averaging losing because flattened by keep the overall tone and tempo over 15 seconds. For our continuous emotion test, this microscopic view is highly accurate. It saves massive memory while still achieving a top balance RMSE of 0.125.
Any other questions?
Hello, how does the PDMA improve the model, and how do you humanity in AD computational overhead to the final companion robot?
FILM is strictly for training. It helps the discriminator tell the generator to learn realistic emotions. However, the generator itself is independent. After training, we discard the discriminator completely. The H model keeps the smart Y but has zero extract inference computation.
Okay. Any other questions?
那个有外国朋友那边我们先讲中文，那个麻烦买那个暗装有没有？暗装要分散一点好不好？感觉起来就作弊的感觉。
Okay, thanks for your great presentation. So predicting balance is significantly more difficult than aerosol. How does your multi-branch gate, particularly the 5GU specifically address this challenge?
Balance depends on ergonomic relationship, not just that. We solve this by applying a DIGRU across the frequency spectrum, not time. Scanning frequency from low to high, that's is clearly model these ergonomic structures. Accurately predicting balance without
change of the random linear to provide you the 1D architecture from scratch instead of applying compression tricks like anticipation to exciting 2D models.
Comparing 2D models doesn't fix their huge memory bandwidth problem. These functions there require billions of operations plus processors to scale and run batteries. By building a 1D module for scratch, we avoid the 2D bottleneck issue, reducing computation by 1,000 times.
Any other questions? Yeah. So we have 4 questions already, right? Okay. Okay, thank you. Okay, we only got the 2 presenters.